Hi everyone! As I promised at the end of the video on advanced post-processing, I'm returning to this technology once again, and this time we'll use it for an alternative method to detect edges in our 3D scene. The result will be an effect that resembles a pencil drawing on paper, which can be a very interesting enhancement for your game. Let's take a look at how something like this works. If you haven't watched the mentioned video on advanced post-processing, I definitely recommend watching that first. You can find the link in the description of this video. In any case, I'll go through all the preparatory steps again this time, though I might not describe them all in as much detail. So let's get started. Once again, I'm using my third-person controller project, which you can download from my GitHub, and I'll include the link in the video description as well. I'll begin by adding the necessary elements to the 3D scene as usual. So we need to right-click here and add a new mesh instance 3D. Very well, and click it to open it in the inspector and assign a new quad mesh to the mesh property. Now I will need to set additional parameters, like size should be 2 by 2 and flip faces must be set to on. Okay, now we need to add a new shader material, and we can do it here in geometry instance 3D section, open geometry and select material override, new shader material, click it again and let's create a new shader. But before we do that, I will increase the value of extra color margin to the maximum. Okay, and now the shader, it's new shader, it must be spatial, and I'll call it, for example, edge, as we'll be working on the edge detection algorithm. Create, create, and click again to open it in the editor. Let's expand that a little bit. Very well, so we have a spatial shader type, and I'll set the render mode to unshaded. Let's do it. Render mode shaded, and the reason is that for the pencil drawing on paper effect we don't need the influence of any light source, and we can see that the flipped faces of this quad mesh are displayed as a white color, so I'll just rotate the camera and we get rid of it. Now we'll need a screen texture and a normal texture. The screen texture provides us with data about the colors of all the pixels on the screen, and the normal texture contains their normal vectors, which are the vectors perpendicular to the corresponding faces on each of 3D model. The reason is that our effect is based precisely on these normal vectors. This is also why we are using this solution with a spatial shader, because in a canvas item shader we wouldn't have access to this information. So let's add the mentioned uniform parameters. Uniform, sampler 2D, screen texture, which has a hint, screen texture, and filter a linear bitmap. And the second one, uniform, sampler 2D, normal texture with a hint, normal roughness texture, and again filter a linear bitmap. Very well, and again, if you are interested in why we use these particular parameters, I recommend watching the original video on advanced post-processing. The next step is to ensure that the quad mesh is always displayed in front of the camera. We'll achieve that using the vertex function right here, and it's just one line. Position is vector 4, which composed of vertex and 1. Okay, now nothing changed. Why is that? This is important. This implementation of the vertex function which I also used last time, works in Godot up to version 4.2, but in Godot 4.3, which I am currently using, the orientation of the Z coordinate in the depth buffer was changed, so this line needs to be adjusted slightly. Fortunately, Godot is kind enough to inform us about this in the form of a warning we can see right here. Let's click. So here it is. You are attempting to assign the vertex position in the model space to the vertex position in clip space. Definition of time, blah, 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 blah. Version pointer is use vector 4 vertex xy 1, 1. This is exactly what we need to do. So just xy, first two coordinates, and 1 for the z. And now this is correct. We can see only white color, but in this phase that's exactly what we wanted to see here. Once again, this applies only to Godot 4.3 and higher. If you're working with Godot 4.2 or an earlier version, use the original code with only vertex and 1. That covers the vertex function, and now we'll dive into the fragment function, where we'll create the actual effect. I'll start by obtaining the color and the normal vector of the current screen pixel. So first we'll define the coordinates. Screen UV is screen UV, as we are working with a full screen. And now the pixel color, vector 4 pixel, is function texture applied on the screen texture and screen UV coordinates. Okay, and the second one, vector 3 normal, is the result of texture applied on the normal texture, and again the same coordinates, screen UV and RGB components, because as we can see, for the normal vector we only need the first three components, because the fourth component represents the roughness value, which we won't be using this time. For the next calculation, we need to adjust the normal vector value a bit. Currently, each of these components is in the range from 0 to 1, but we need -1 to 1, because that's what we will what will be required in the algorithm using the Sobel operator, which we'll get to soon. So first we need to multiply the vector by 2, which will return a range from 0 to 2, and then subtract 1 to get a range from -1 to 1, like this. Normal is normal multiplied by 2 and -1. This simply means that we are working with vectors, so we are multiplying by 2 and deducting 1 of each component of this vector. You might remember from another one of my videos on edge detection that we needed the pixel dimensions for the algorithm to work correctly. This time we are working in 3D, so instead of screen pixel size, I'll use the viewport size, specifically its inverse value. Vector 2 pixel size is 1 divided by viewport size. That's because we have a spatial shader, so the mentioned screen pixel size is not available here. We are working with a viewport size. It's time to apply the Sobel operator. I discussed this operator in more detail in the edge detection video, the link to which you can also find in the description of this video, so the algorithm remains the same. We start by creating a 3x3 matrix, which we will fill with values for all the neighboring pixels of the current pixel. The value will be the difference in normal vectors, which means between the neighboring pixel and the current pixel. We will create this matrix using two nested loops. So first I will define the matrix 3, and call it pixels, and now the nested loops. First one, 4 int x starts at -1, x to 1, and x plus plus. Okay, and I need to create a vector for the particular row, and now the second cycle for the integer y is -1, y to 1 and y plus plus. And now inside of the cycles we need to define the offset for the particular pixel, which would be vector 2. Offset is pixel size, as it depends on the calculated pixel size, multiplied by vector 2. And now we need the x and y indexes, but this time we work with floats, so we need to convert them. Float x and float y. Okay, and let's define the particular cell of the matrix, which is a vector 3, and it contains the normal vector, so it would be texture applied on the normal texture with coordinates green UV increased by the offset to get the neighboring pixels, and again RGB components. And now we can assign the difference of these vectors, which will be the length of the difference. So row y plus 1, because y is from -1 to 1, but we need indexes 0, 1, 2, is length of the difference cell minus normal. Okay, and finally we can assign the final row to the matrix, and again x plus 1 for the correct index is row. Great, this is it. Okay, there is a typo, of course not plus sign, by equals should be here. Very well. You might remember that in the original edge detection video I used an array of 9 elements instead of a matrix. Both approaches are valid. However, this time a matrix is more suitable for us because it is composed of vectors, which we will use in the next step to compute the dot product. The following lines are also a part of the Sobel operator algorithm and are described on the relevant Wikipedia page. First, we'll define matrices for computation in the x and y directions. Since these are constant values, we can declare them as constants right after the uniform parameters. And to save some time, I will just simply paste them here, so we don't need to type everything online. Sobel x and Sobel y matrices 3 by 3. And now the mentioned calculation right here. So I will create variables gx and gy, which came again from the Wikipedia page about the Sobel operator algorithm. Float gx, it starts at 0, and now we need a cycle to define it for int I from 0 to 2 and I plus plus, and gx is increased by dot product between the Sobel x matrix and the index I, so it's a vector, and the second vector is from the matrix pixels. Very well, this is the gx, and now for gy, copy paste and change it to gy here and here. Cycle is the same, and we are using Sobel y matrix. Great, and finally we will calculate the value which I call simply Sobel, and it is the square root of the second power, so gx by gx plus gy by gy. Great. We obtained a result that allows us to decide whether to draw a pencil mark for a given pixel or to display the paper as the background. However, we first need to define a few additional parameters. We will need a threshold for this decision, as well as the pencil color and the paper color. Let's add these parameters to the uniform parameters section. Okay, so it would be a uniform float threshold with a hint range and initial value set to 0.5. The hint range is from 0 to 1 and 0.01 as the step. And now the colors: uniform vector 3 line color with a source color, so we will get the color picker in the inspector, and let's start at 0.4 for all components, so it's a shade of gray. And similarly, uniform vector background color, source color, and initial value would be 0.9. I chose slightly grayish pencil and not completely white paper as the default values. The result looks better than pure black and white. Of course, you can set the color combination that suits you the best. And now, finally, we can assign the final color to the current pixel, which we can do in a single line. And since we are working with a spatial shader, the variable is not color, but albedo. Albedo is, and if sobel is greater than threshold, let's use line color, otherwise background color. Let's wait for it, and yes, here we go. We are done. We can play around with the threshold parameter and see how our effect changes. So I increase it or decrease it. We can set it exactly as we need in our project. By the way, this is another advantage of the spatial shader over the canvas item screen reading shader that I used in the first edge detection video. This time, we can see the resulting effect directly in the 3D editor, whereas in the first case, we had to run the project first because the 2D shader had no effect on the 3D scene in the editor. Thank you for watching, and I hope you enjoyed delving into the third dimension for a change, given that the vast majority of our tutorials cover 2D shaders. Both technologies are very interesting, and I'll definitely revisit 3D shaders several more times in the future. For now, I wish you great success with your projects, take care, and I'll see you in the next video.